Hi, everyone. Can you hear me? Fantastic. So thanks for introduction. I want to talk about explainable forecasting using causal inference. So let's review some materials we need for this discussion. So I want to talk about the explainable AI. So more specifically in high stakes or high risk environment based on my experiences. Explainability means sometimes is important as much as the accuracy when talk about the AI models. Forecasting is a high demand initiative, more specifically in finance. Causal inference is a tool for reasoning, more specifically in AGI and for explainability. Explainable forecasting means how we justify the predictions through the what-if scenarios. And storytelling, that's how to bridge between mind and machine. So, but the thought process for my presentation is we need a causal inference to provide explainability and then do reasoning and then storytelling and then action. Because the environment we are working on, most of the decision makers, they are not familiar with AI. They don't have background in AI or any things. So you have to provide the end results as much as possible simple and straightforward. So that's the whole thought process. So based on my experiences, I think the world of AI should be divided to two completely different worlds based on the cost and risk of the errors. So I just provided some fuzzy categorization between the low risk, medium risk, and high risk, but you can do yourself. I mean, that's my perspective based on the experiences. So when going from the left to right, by decreasing the hype, there is a necessity for explainability. And that's because of the cost or risk of the associated the risk or cost of the errors. So for example, in binary classification, you have a false alarm, false positive, false negatives, or in multi-class classification, you have a much more types of the errors. So each errors could be different and behave differently. And when you're working in the high stack fields like finance, aerospace, supply chain, healthcare, cybersecurity, and so on, that the errors is very important. So explainability necessity is getting much more important. So, so I have a talk last year in NeurIPS conference that I tie explainability with the error monetization. So I mentioned that if you want to successfully deploy a model in the highest stake fields, you have to have a clear cost function. That was the point. So AI may soon know more about humans than we know about AI. So based on the current tendency, trend in the AI fields, very soon AI could be our team worker and group colleague. You have to understand AI if you want to work with AI in parallel. So we can see the explainability from different perspectives. The degree of the interaction between the human and AIs. AI then can generate for you, or chat for you, or do for you, like agents. So depends on the level of the interaction between human and AI, the explainability getting important. So for explainability, we want to answer a bunch of questions. For example, counterfactual questions. How and to what extent small and plausible changes in the input affect the output, you know? So why does the model make specific prediction or outcome? So that's the type of the question always you want to answer in terms of the explainability. So why causal inference? Causal inference is a very good and robust and straightforward AI explainability. So in the current practice, causal inference, we have a huge literature around the causal inference. Mostly, causal inference is used for feature selection and extraction before training. So in the chart I provided here, so I show that before training, you use the CI, or causal inference, for to select the features, and then train and forecasting whatever model you want, and then provide explanations through the other methodologies like Shapley value, line value, F-score, or you name it. The problem is that most of the time there is no consistency between the CI before and after training. That's, I refer it as a Rashomon gap. Rashomon gap means several good models provide different explainability. That's a confusion. That's a problem. I mean, based on my experiences, you can run a bunch of the models, you get the very good results in terms of the calibration and whatever, but you have different explanation. Shapley value is not same as causal inference and so on. Yeah? So that's why, even if you are very good in the prediction, you are losing your audience because they cannot trust your model, because you cannot provide a single concrete explainability for the model. So the question is how we can integrate all of them at the same step, using causal inference instead of feature selection directly for prediction. Explainability, prediction at the same step. That's a point behind my presentation. So causal inference, if you have a problem here about the definition of causality, we know correlation is not causality, but we don't know what is causality exactly. I mean, there is no unique definition for causality. Depends on the usage or application, you know? Causality is a type of directed association, we know, but association could be anything. Could be linear, nonlinear, monotonic, non-monotonic, very complicated behavior between two variables, you know? So we have a different perspective for causality. We have a statistical perspective, say variable X affect Y. If given information Z, X and Y become independent. We have a deterministic perspective that X always affect Y. That's we say true causality. Or we have a physical definition that X affects Y, but not always at the specific level. There's a kind of interaction between the variables. And we have a bunch of considerations here. So for example, time series is a sample observation in equals time distances with regular time interval. Contemporary versus time lag causality. Pair dependency versus more complicated form of the dependency. Hidden or unknown variables or confounder, or we say latent confounder variables. And also we have a mixed data types in most of the real world scenarios, like a semi-continuous observations, discrete events, or domain knowledge experts. Sometimes you need to combine all of them at the same, in the same application. So as I mentioned, current usage for causal inference, mostly used for intervention or treatment effect estimation, and attribute feature selection, a pre-training phase, as a pre-training phase. That's the current situation, actually. So how we represent causal discovery or causal inference using the causal network, or DAG, directed cyclic graphs. For example, I provided a couple of examples in macroeconomics environment. So, for example, tariffs affected government spending, supply chain disruption, natural disaster, that's an event, affect the supply chain disruption, and government spending affect the demand pull factors and so on. So the DAG is a good way to represent the causal discovery or causal relationship between the pair variables. So the solution we provided is transition from CI-based feature selection followed by forecasting to models designed inherently for explainable forecasting. So we try to combine explainability and forecasting at the same step. So how we define the causality? We use chi-correlation. Chi-core is a methodology that recently, that was a publication I think 2 years ago, that is a kind of rank-based methodology to find the relationship between X and Y, between the pair variables, based on the ranking of the data. The chi-correlation measure how much Y is a function of X. So the goodness of the chi-correlation is similar to a Spearman correlation, that you can detect monotonic using the Spearman. But the goodness of the chi-correlation is that you can also detect non-monotonic relationship between the variables. So chi-correlation is a directional correlation. Y could be a function of X, but not vice versa, always. We use this definition to measure the causality between two variables. One of the advantages of the chi-correlation is, the first is capturing non-monotonic relationship as well as monotonic. And the second one is asymptotic property, that by having a large enough sample size, chi-correlation statistic approximately follows a normal distribution. That's one of the goodness of the chi-correlation. So, if you have a time series, so the robustness of causality is very important, because you want to see the causality over time and see the behavior of the causality is fixed or remains same between pair variables or not over time. So we use dynamic conditional correlation, or DCC, along with chi-correlation to capture robustness in the causality. Robustness means a strong and a stable correlation or causality, chi-correlation or causality score over time. So if you look at the graphs I provided here, the color of the points represent the timing of the data points over the time. So dark blue represent the more recent data points, actually, and try to capture the causality over the time. That's a sample chart. Using the chi-correlation, we can estimate the causal impact. So we need to do some mathematics, but I don't want to go deep. So if you look at the left side of the slide, we can say X cause Y if Y is a function of X, but not vice versa, given a specific threshold. So I provided the graph here, so you can see that's, for example, I provided here, that's XY, whatever, here. Y is a function of X, is like that's a quadratic core, but not vice versa. X is not the function of Y, because it's not anymore a function, you know? For prediction, we use the Kolmogorov Allnort representation theorem. That's a methodology to learn causal relationship as a functions on the graph DAG network. Kolmogorov Allnort representations based on this representation, any multivariate continuous function can be expressed as a sum of continuous univariable functions. That's very good for modeling complex nonlinear relationships in time series data. But we have a very important assumptions here, that a non-function relationship indicates the existence of a latent confounder, that the variables we never, I mean, the assumption is that if there is no non-monotonic or monotonic between the X and Y, that means there is another variable like a Z that's a latent confounder that we cannot capture it. I mean, one of the goodness of this approach is that you can estimate the number of the variables you never capture in your model. So each causal age here is represented by 3 parameters. First, causal impact, second time lag, and third one is a causal function. So the pipeline for implement this process is first, construct association matrix, how much Y is a function of X in terms of chi-correlation, and then construct causal DAG, to what extent X causes Y, and then determine causal relationship, the functions between the pair variables, how X causes Y, and then we can do prediction and both answering the explainability questions. For example, how and to what extent do plausible changes of X modify Y? So it's a counterfactual questions. So based on this pipeline, we have everything at the same pipeline. Explainability in terms of the causality and the prediction at the same time. So how? So let's show you some results. So to show the results, we use data sets that's used for predicting Canadian macroeconomic factors. Is available online. We use 124 Canadian factors plus 3 US factors. The data is coming from StatCans Canada. The data include GDP breakdowns, CPI breakdowns, customer price index, labor force characteristics, interest rate, housing price index, mortgage interest costs, and so on. The size of the data is 20 years monthly observations. And we use this data sets by purpose because of the complexities or challenges behind the data sets. First of all, this data coming from the economic finance. We have a lot of exogenous and latent variables that we cannot capture. Traditional ML models cannot predict perfectly this data sets because of monotonic behavior between many variables. Monotonic behavior that result that ML models struggle with trend extrapolation when the test set is outside of the range of the trained set. That's a complexity behind this things. And each macro factor in the network, in the causal network, is a different animal because it has a completely different statistical characteristics. So we did some pre-processing, like a COVID extrapolation, to remove the shock because of the COVID from the data. But how we tune the network, the causal networks? So we use fact check. For example, we know US economy greatly or highly affected Canadian economy, but not vice versa. So we use this fact to tune the model parameters. And so after tuning, that shows that GDP of US affect the CPI, the US, and then affect the CPI shell Canada. CPI, as I mentioned, is customer price index, and CPI shell Can is a good proxy for a housing price and housing market. This is a causal network constructed causal networks based on different scenarios, based on different threshold of the chi-core correlation. Left side is a conservative scenario. The middle one is a moderate scenario, and we have a progressive scenarios that we have a lot of. When you change the threshold of the chi-correlation, you can see a lot of correlation between the variables. The variables divided to the source, intermediate, and sink. So, for example, you can pick one of the sink variables and then try to forecast it. So we pick one of them and try to forecast it using this methodology. If you see that we are very good in the trained set, but not perfectly in the test set, because the distribution of the test set never seen in the trained set. That was the one reason we choose this data sets. So the goodness of the approach is that you have prediction plus prediction interval, not confidence interval. Don't miss it. Prediction intervals is very explainable. That means which variables result in the upper bound and lower bound of the prediction. That completely differs from the confidence interval or conformal prediction, conformal intervals and similar things. It's completely different. So you have a prediction bound, but you can explain it because you can see, based on the table I provided here, you can see which variables or which cause of the specific variable result in the upper bound or lower bound of the interval. So that's another more result of the prediction. So for some variables, we get a much better outcomes. But the explainability, So one thing we can check is how a spike in the data sets can cascade over the causes across the causal network. You know, for example, in A, cascade impact over causal chain A to B to C. So if you see there is a volatility spike in A that affect the B with 1 time lag, and then affect the C with 6 time lag, based on the train network. And the right hand figures, you can see dynamic causal interactions. So if you see the causal interaction between the variables A and B is not fixed over time. More specifically, the bottom figures, the B to C has a stable causality over time, but not vice versa. If you see the C to B is different and change over time. And you can put another layer like a new sentiment or so on to understand why that's happened. That's actually the next step we are working on this project. So, takeaways, pros and cons, simple and straightforward for explainability. That's very important because you can use other type of explainability, like I mentioned, like a Shapley value, like a Lime, so on. But if you use that parameters, you need to add another layer of explainability to explain the factors. So causality is very similar to the human cognitive progress. That's why it is simple and straightforward. You don't need to create crazy features to explain the model. Robust to change in data distribution, robust prediction across the causal network, explainable uncertainty quantification. As I mentioned, you have a prediction interval, but you can explain the prediction interval that which features result in the upper or lower bound of the prediction. No need for retuning model for various target variables in the network, and distribution-free prediction. And you can explain the tail events and so on. I mean, there is no complexity behind it because we try to make it simple as much as possible. But what is the cons is the cons of the model is complex nonlinear relationship cannot be detected definitely because we assume everything as a function. The non-function relationship doesn't work here. So, but the goodness is that if you see a non-function relationship in the network, that means there is a hidden variable that you cannot capture in the model. Thank you. I tried to make it very MP3, but hopefully that was useful.
Thank you. Great talk and great interesting results. So when you mentioned that you had the dynamic relationships when A was causing B and B was causing A, how did you deal with that? So because you have the violation of DAG, so it's no longer acyclic, it's a cyclic graph. How did you deal with that? Do you have any specific methodology?
Thank you. This is not dynamic graph. We see the dynamism before creating the causal graphs. If that's a part of definition of a causality. The causality robust causality means if there is a age between X and Y in the graph, that means X affects Y in terms of correlation and is stable over time. That's why I'm not talking about the dynamic graph. I'm talking about the stable graph, but stable over time. Yeah,
but just a follow on there. So in your example, there was GDP was causing interest rates, but we know in economics, and that's why economics is so difficult, is that because interest rates also affects GDP. So how do we solve that problem?
Actually, there is no loop in the. That's a cyclic graph. There's no loop in the graph. But maybe you can see multiple paths between two things. So you can explain it. If there is a multiple path, so I don't know, I can show it again anyway. So if you see the time lag, and the time lag explain the multiple path between X and Y. So yeah, that's possible that X affect Y through different paths. But should be compatible. The path should be compatible in terms of the time lag between the variables.